start recording this too. So characteristics and brims, that's our two interactions that happen in the tube. Today, we're going to talk about what happens after those photons leave the tube and the happening of in the patient, what's going on. So we're still talking about interactions, but just in a different way today. The next one, Michael, what is a dual focus X-ray tube?
Dual focus is when it has two filaments on the cathode side. There's the small one for less heat and smaller body parts, and then there's the large filament for larger body parts, a bigger beam, more heat.
It'll be more spaced out with the large filament, the electron stream coming across, which makes essentially a large focal spot on the anode. Tighter, smaller filament, tighter electrons coming across, which makes a small focal spot on the anode. So our actual focal spot is where they hit, the AFS. Then therefore reducing the beam to the effective focal spot, which comes down, and we'll talk more about that and the reason why we do the small one on small parts in another class, another day. We haven't gotten there yet, but we're almost there. So our next question, Sarah. What does mass affect? How does mass affect the quality of the X-ray beam?
Mass is the primary controller of quantity, but if you increase that, it increases the quality?
No, but you were partially right. Mass is the quantity.
That's what I put it first, and then I was like, wait, is that it? Like it doesn't affect I couldn't remember.
Not do quality at all. So people get tricked up on this one all the time. So mass is the heating up of the filament, the current, heating it up. That's how many electrons we boil off. So it therefore tells us how many photons can be produced. But quality is penetration. That's the energy of the beam. That's controlled by the potential difference, the attraction over. So quality is only how much energy they have, and mass doesn't do anything with that. Mass only has
I took it as more as how could it affect quality. So the increase in amount of electrons produced for the X-ray beam, that doesn't increase any kind of good photon that could possibly penetrate.
It doesn't do anything with the quality, which quality is energy. It doesn't do anything with energy. It only does something with the number that we produce. All of the quality is kVp.
Yeah, so, but each electron that turns into a photon has energy, right?
Yeah, but changing mass, making more mass doesn't change the quality of that photon, but
could it produce a photon that has more energy? Like
only kVp can do that if we increase kVp. So if we say 20 mass or 40 mass, we're still going to produce the same number of photons with that same equivalent average energy, depending on what the kVp is, if that makes sense.
Oh, isn't doubling kPV the same thing as, or increasing it by 15% the same as doubling the MAS?
We'll do the same thing to the number of photons. Good. kVp affects the quantity of photons getting through the part or to the IR by, if we could say it's doing the same as doubling the mass because we're doing twice as much. That's another whole question we could ask. How does kVp change the quantity of photons getting to the IR? And we're going to talk more about that today too. But that's the other end of it. That's the quantity. kVp affects the quantity because more penetrating, more X-ray photons can make it through. We increase the energy. So I guess that was kind of tricky, that one.
Right, and then I just kept talking. I just loved it at that.
Just loved it at that small part, yeah.
Like, that's a weird one to put as a trick question because
I didn't even mean it to be, but
well, I know, but the way it's
multiple choice, people miss that one. It'll say what affects the quality, and mass and KVP will be your choices and some other stuff. But mass gets picked. Mass does never, ever, ever pick mass for quality of the beam. Mass is only quantity. Because you can up your mass, up your mass, up your mass. You're not changing the energy. You're only changing the number of photons being boiled off, number of electrons. I need to copy something real quick. Next question, Tawala. Let me see what the next question was. I think this one was an easier one. What is it meant by the intensity of the beam?
I said the quantity or the mass, the MAS.
So it's the quantity, and that is controlled by mass.
Mm-hmm.
Good. Intensity is how many photons or how many electrons we're boiling off. I think some people put that, either one. Good. I'm not. Holly. The next one. Does the penetrating power of the X-ray beam describe quantity or quality?
Quality.
Good. So when we describe penetration of the beam, that's our quality of the beam. How much energy does it have? Is it more penetrating or less penetrating? And we sometimes want a lower energy beam, and sometimes we need a higher energy beam. So that's why we change our kilovolts. Now, does the quality of the beam, this is getting to what we were just talking about, change the quantity of photons making it to the IR? Yes. So we can say that quality affects quantity. Our controlling factor for quantity, though, is mass, but other things can change the quantity of the beam, just like other things can change the quality of the beam. So you kind of got to know all of that, too. Quantity is controlled by mass, but if we increase KVP, we're effectively increasing the quantity reaching the IR, and we'll talk more about that today, too. If we add filtration, we're getting rid of low energy, so we're increasing our overall quality of the beam, making it a more higher energy beam. So filtration affects quality and quantity. And we'll get into that more coming up. And on this next exam, there'll be more questions relating to that. So just to keep talking about these things from last week. Jonathan, what's my next question? This one's for you. What are the 4 criteria required to produce X-rays?
The requirements to produce X-rays are a vacuum, a source for the electrons, a target for them to slam into,
Yep.
and their potential difference.
Good job. So they need a source to be boiled off. They need a vacuum for it all to happen in. They need that high potential difference, and they need that target to slam into. I think a lot of people got that one right. Good job. Next one. Janelle. What or where does thermionic emission occur?
It occurs in the cathode.
I'm sorry, what'd you say?
The cathode side.
You could have said the cathode side, at the filament. Some people put inside the focal spot, and then some people described it. Thermionic emission happens at the filament when electrons are boiled off. That is the whole definition of thermionic emission, the boiling off of electrons, and that happens at the filament. And this one was for all of you guys that wanted the properties of X-ray. Kaylee, what are some of the properties of X-ray?
So this question was meant just list 4 properties out of the 12, right? Okay, I was highly confused. I didn't know what you were talking about. But in that case, it's ionizing matter, highly penetrating. They travel at the speed of light, and they can't be focused by aliens.
Good. So lots of other things that they can ionize. They only travel in straight lines. There are many, many energies. They're invisible. So there was 12 properties of X-rays, and you just had to list 4. All right. What is that? 40 starts this mess. The next person, Kevin, have I called on you? Oh, this was a chapter question. So the interaction that happens in the patient that results in the photon being absorbed by the patient, that is called photoelectric.
Electric. I looked at that. I almost got that right. I was going back and forth between that.
I did too. I had it, and then I was like, I don't, because I didn't read it. I won't lie. So I chose something else.
So some people already did their objectives for the homework for the week. That homework for the week for this week is not even due till Friday, almost like late Thursday. Now you can't do all the objectives, but they started on it, and I was like, wow, they're going to get that question right because they already went ahead and did the whole objectives for the chapter. So those objectives, again, I wanted to talk about that today. I posted last week and it had the wrong date, so I guess that's why they did it, because they thought it was due last week, but it's actually this week's homework in week 2. I edited it. So now hopefully the right date is showing for you guys to turn it in at the end of this week. It's for the ones that I have posted in the folder. Every day I have the objectives for what we're going over that day. And you can just take those, kind of make a little bullet or outline them however you want to do it. And I also created a journal for you guys. And this journal is in Blackboard. I think you'll find it under, let's see what it's titled on my end, so you can tell me if you see it or not yet. It is under course tools for me. And it says journals. So it's basically like a little place you can type your notes and things into for me to see. If you have any questions and you want me to go look at it, I can reply to you back in it. It's only for you and me to see. You could start your homework on a journal entry and then keep adding to it each night and then copy all that over into the assignment. You can do it on a Word document. You don't have to use the journal for that. But I just made that for everyone. And then I had some people that I have for tutoring to type questions to me every day after class, anything that didn't really make sense, or if you're at home and you're wanting to ask me a question, you can put it in there and just let me know and I can go in and reply to it. So that's something that you're going to actually test out now for me. I have a entry that I want you to do.
You said that you don't have to do it on there?
No, you don't have to, but this I do. I want to test it out, and I need this in writing from everyone so that I have it documented. So I have something I'm going to have you guys do in there right now, just so I will have it documented for my use to have. So I'm going to share my screen so you can see what I'm talking about. Maybe it's going to get big. There we go. So I don't know if you can copy from this, but basically, want everyone to be sure they know the rules and policies for these things that are important, that I have a few things that we keep having issues with. So we're going to take 10 minutes now for you to read over this. This is my kind of example of it. And put it into the journal for me. At the bottom, type your name saying you've read it and understand it. If you don't know where to find the rules, they are in the handbook. So anytime you're going to be absent or late, even if it's an emergency, instead of texting, I need it to be emailed to me so I have it documented. If you have any questions about what our dress code is, that's kind of my summary of it. The most things that people have that they break that are in the dress code policy. Sometimes it's artificial nails on girls because we can't have them in clinic, no unnatural hair colors, no excessive jewelry or perfumes. There's a lot more detail in the handbook, but these are the main ones that happen. And then the attendance policy, just to let everybody know, if you miss 3 days, you cannot take the final. I don't know if you remember hearing that from the rules. So if you're late or leave early and you do that multiple times in a class, that counts as 1 day absent. So if you miss 3 days or late 3 days, that counts as an absent for our policy. I will type up a letter. If you miss 2 days, I will type up a letter and send it to you and let you know 1 more day, you're on the verge of not being able to sit for the final. In clinic, it's a lot stricter. In clinical, I believe it's 2 days, but you can see the handbook for more info on that. Ms. Stelz will be going over that with you. And then this testing policy wasn't in the handbook, I don't believe. This is something that just as a program, Ms. Dean has had for us forever and ever. I'm pretty sure most classes it's like that, but I don't know, some might let you copy or share the exam. But anyway, I told you guys about it in 1000. I never told you about it here, but I never had it in writing that I gave you the rules. So this is my giving it to you in writing, copy it down, sign it in this journal entry. The only thing allowed on the desk during a test is a calculator, and you cannot afterwards when we review have any kind of copying of it. So if it's done online, you can't save it or download it or anything like that either. Any copying is considered academic dishonesty, and in that you can see the handbook for the college, the university policy on that. So just copy this, retype it in your own words, however you want to do it, into the journal and sign it. So I have it documented that you have been told these rules and policies. Once again, you have signed all the dress code and attendance policies with Ms. Dean when you started the program in that signature packet, but it seems like maybe people didn't really read it or something, I don't know. But these are for you guys to once again refresh on the main rules. And in the classroom, we also have, I didn't put in here, but no food or drink allowed. So even if you're on break, snacking, eating food is not allowed. And that's a Kaiser campus president rule. We would love to, especially Ms. Stelz and Ms. Dean, have coffee in the class, but we're not allowed.
Where is the journal at?
So if you look in, anybody found it? Because I have it under that place. I'd have to stop sharing to go back
It's
and
under ours is tools. You go to tools and it'll list a bunch of stuff up and it says journal.
Yep, there you go.
Okay, I see it.
So can we just write that, you know, our name, understand the class and program rules with regards to dress code, attendance, and tests, exam,
Whatever
quizzes?
you want to say, yes. Yep.
Okay, wait. So you said it's under tools.
And it says journal. There should only be a few little links there.
Okay, I have announcements, application authorization, Everglades Smart Thinking, online tutoring, goals and assessments, portfolio, send
Can you look on the right hand side? Does it have the journal on the right hand side?
I'm looking under tools.
Tools is located down where the grade book is, over to the left-hand side of the screen under groups.
The grade book area at the bottom. So scroll down on
And
the
there's
left.
2 rows, like the row she was reading is on the left-hand side. Mine has a whole.
Got you.
Yeah.
Now, where will we find this that we can copy it from, Miss Love?
I just typed this up a little bit ago. Let me try to see if I can copy it and put it into a text message thing. Let me stop sharing and put it into the chat. Oh. Big. Stop. Okay, there it is. Now you should be hopefully able to highlight it and copy it.
Miss, please forgive me. Where did you put it at?
In the chat of the Zoom.
Oh, okay. Thank you.
Are we doing chapter 7 and 8 today, or just chapter 7?
Just one chapter 7.
You couldn't paste the entire thing, so it gets cut off.
Oh, it did? Okay. Let's see where it stopped at.
When we review the exams, that is.
Okay. Let's do that one on its own.
Do we have to name this a certain?
No, it's fine. As long as I can go back and print it out if I need to, that everybody has it.
And at the end, you just want us to type our name in?
Just that you understand it.
Okay.
Yep, just type your name on it that you understand the policy.
Ouch, but I don't like it.
So just kind of highlight, copy this, put it in there, and that you understand it. Yep.
So what was the answer to that the read ahead question?
Photoelectric. It's called photoelectric effect.
It's not letting me
You already typed it before I did the page, then you're fine. It's not letting you do that?
not in the message.
You have to use Control V.
Oh,
Okay.
yeah. Control paste. Yeah, okay. Just look and see.
Miss Love, do we type it in the submission box or like upload it in a file?
No, just type it in. You don't have to upload anything.
Okay.
Oh, it's trying to get me to post a journal entry. I can't. I think I set it to not let me look at it till after 3 have been Okay, there we are. Do a comment, I'll paste it. All right, so I think you should be able to come back into it, add more if you want to add notes after class. So you have it all in one place. You can copy your objectives in here and put them along as we go over it, and then copy them all into the assignment at the end of the week. However you want to do it though. I mean, you can do it on a Word document and then upload it too. But this is just if you want me to come back and check on a question that you might have for class between after we get off the live and 1 p.m. and you want me to come back on and answer it throughout the day, you could message me and say you put something in the journal for immediate help if you had a question. So that way it'll be easier for you to have all your stuff in one place.
I think mine went through just fine.
Yeah, it looks like everybody had posted into it, so it looks like we're good.
So we're just using the journal, like if we need to get in contact with you or anything like that.
Or for your own studying. I mean, if you wanted me to answer a question you had, you can let me know. You put it in the journal and I can reply to it. And then if you're taking your notes and keeping them there for the weekly objectives for this week's assignment, you could do that every day and add to it and then copy them over to the assignment. And then I would be able to give you feedback in case you wrote something wrong and I see it, I can catch it. All of the worksheets that are there for the weeks are worksheets, just some of them I will give you in class to fill out. If we're on campus, some of them we'll go over together online. Some of them are just there for extra help. They're not anything you have to do unless I put it in the homework folder.
So Miss Love, as I look at the homework that you posted on here, it has Monday, Tuesday, Wednesday, and Thursday. So those are all due by midnight on Thursday, correct?
Yes.
Okay. All right.
Yep.
And we're just doing the outlining on this, right?
Outline or notes of all the objectives for the week. Yep. This will help you for the final, for what you're going to need to know.
Okay.
And I just pulled these objectives off of your syllabus. So the syllabus lists all the little bullets for the whole class. I just broke them up into what we're going over by the chapters. So some of these actually overlap. You'll see something on here twice. You don't have to do it twice. I think it's the one that talks about the 15% rule and the exposure. It's kind of doubled up on today's objectives, actually. They just ask it in two different ways. As long as you have something bulleted for the 15% rule or for exposure.
All right, thank you.
Mm-hmm. All right, so let's look at this chapter in the book. We're talking about interactions in the patient. So we talked about tube interactions last week. Get to the chapter here. And this week it's called Interactions with Matter. So we're matter, we're the patient. It could be a phantom though, like we use in the lab, that's made up of atoms and matter in it and made it to seem like it's a real foot. It has the density and makeup of a foot with bones and soft tissue and everything, as we saw in our lab last week when we did those exposures on the phantom, the foot. So when we're talking about matter in this case, we're usually talking about a real patient though. So chapter 7 is called X-ray Interactions with Matter. And there's some bullets in the chapter, so I don't want you to get confused with the objectives for the week for class and these objectives for the chapter that the book put together, because some of these items we're not necessarily going to focus on right now. In this class, we kind of skip some of the items in each chapter and push that off to a later class. And there's a couple of things in this chapter that we're not going to go over. So you don't have to know all of the book objectives, only the ones that we talk about. Mainly in this chapter, it's the stuff about DNA and the chains being broke and things like that. You have a whole radiation biology class later in the program where you'll go over all of that. So first, you need to know what happens in the tube, the 2 different photons that we make in the tube. But really, we don't care about them as much when we're talking about a picture being made. We just know in our head that some of those are Bremstrong, some of those are characteristics. So really, that interaction in the tube is just for the registry about what type of interactions happen in the X-ray tube. So 2 types, characteristic and Brems. Don't ever forget about them, because you don't really talk about them much more going forward. The ones in this chapter are going to be talked about a lot in a couple of other instances, mainly the Compton and Photoelectric. There's another one in here that we don't talk about very much. So Compton and Photoelectric are our 2 main ones. So let me share the screen and we'll go through the PowerPoint of the chapter. And I just call these patient interactions. So we have 2 X-rays here on this screen, a chest X-ray and an abdomen X-ray. And this one actually has a mass or a tumor in this big white spot here. This other big white thing's the heart. And you can kind of see a black shadowy line coming down. That's the trachea. And if you follow it here, you can actually see it coming down into the lung, the bronchial, the bifurcation of the trachea going down. This side, not so much, because it kind of leads right into the lung. This one kind of takes a turn and goes here. And plus we have the heart overshadowing it that makes it show up a little bit like a little black line. Takes a long time to look at to see that. You can also see all the black of the lungs. Some people see this X-ray and like, oh man, I need to quit smoking. All my lungs are black. That's air. Air shows up as black on a radiograph because it's radiolucent. So the X-rays went through easily and came through and penetrated onto the image receptor. It doesn't mean that all this black is from smoking, but that's what patients think when they see a chest X-ray. Then we also see bones. We see the clavicle and the ribs. You can see the ribs kind of curve around in the front and the back. So we're seeing doubling of the ribs, the front and the back of the ribs. You can see the scapula here. If you really look, you can actually see it over on the inside of part of the ribs. You can see the shoulder joint here and the humeral head here. You can really start to look and see things the more you look at it. Now on the abdomen X-ray, the abdomen has a lot of organs in it, the intestines, the liver, the kidneys, all of our muscles of the abdomen. So an abdomen X-ray kind of has a lot of stuff going on here in the middle, but we can't really make up too much or see it because it's all similar in what the atomic numbers are. Now we can see big black splotches here. That's the air and the gas in the intestines. And you can kind of see the little shape or the bubbles of the colon. You can see the spine, you can see the little processes coming off the side of the spine, you can see the processes coming off the back of the spine, nice pelvis and hip. In the middle, the circle, there's our bladder sitting in there. We can't see the bladder unless we put contrast media in it. You can kind of see some of the colon splotchiness here with fecal matter in it. See the sacrum, the holes in the sacrum, the little black circles. So lots of things you can see on an abdomen X-ray too. But there are 2 different types of shades of gray and blackness and whiteness on here. You can see a lot of different close shades of gray here. You can see these stripes, this line that looks like a stripe coming down. That's a muscle, psoas muscle in the abdomen. You can see this fold of black here. This is belly fat with air in between it, just stripe going across here, roll of adipose tissue. So lots of things that you'll be able to pick up on X-rays differently on patients. You can see soft tissue of muscle here in the hip. So when we're talking about interactions with the patient, we're talking about everything that's going on as those X-rays are passing through the patient and how do we get these shades, either black, white, or gray, to show up. So 5 different things can happen when X-rays are going through and interacting, depending on their energy. classical scattering, Compton scattering, photoelectric effect, pair projection, and photodisintegration. The first three happen within our diagnostic range. The other ones are way, way high outside of the energy level of what we're going to be using in X-ray. So in this drawing, you'll see it a couple times. This is our X-ray tube. X-rays are coming out of it, going through a patient. Some of them scatter off in a new direction. Some of them make it through to the IR. So we're going to talk about what these all are called as that's happening. When the beam's coming out of the tube, this is all of our beam. This is our primary X-ray beam. So what's coming out of the tube is our primary beam. What comes out of the patient is not the same amount of X-rays as what we started with in the tube, because stuff happens to them. What comes out here is called the remnant beam, or the transmitted beam, we'll call it, what gets transmitted through. So these first three interactions we're going to talk about now. Classical scattering. This one has a couple of different names, so I don't know what the registry is going to ask about that. So you want to know them all. Classical could be called coherent or Thompson scattering. This interaction happens with super, super low energy, less than 10 keV. keV means kilo electron volts. That's the energy of that single photon. Remember, kVp is our maximum volts going through the tube. We can give each single photon an energy level that's going to be measured in keV. So we could have an energy of 0 all the way up to the maximum kVp we set. So if we set 70 kVp, our beam's going to be anywhere from 0 to 70, with an average energy being 1/3 of the kVp we set. Remember that from last week. The average energy is 1/3 of what we set. So if we set 100 kVp, our average energy of the beam is 25. So some of our X-rays are going to be 0, some of our X-rays are going to be 100, and most of them are going to be 25. That bell-shaped curve, that would be at around 25 keV. So those ones that are close to 0 to 10 keV are going to be this type of interaction, classical. These low energies are going to come out and go through the skin of the patient, and they're probably going to barely get through anything because they don't have a lot of energy. So if they come out of the tube, they're not going to ionize because they're too low of an energy to interrupt or knock out one of those electron shells. So remember, ionization is an adding or removal of an electron. So classical doesn't do ionization, but they're just going to absorb and cause excitation of the atom and go off in a new direction. We don't get any useful information out of these. They'll just be absorbed in the patient. So we don't want these. They're not helpful. So we get rid of them before they can get to the patient by filtration in the tube. So that's 2.5 millimeters of aluminum instead of all these low energy coherent or Thompson scattering from happening. So we don't have this, hopefully, happening in our patient's skin. So does that make sense? That's why we have that added filtration, that aluminum and everything in the tube. So those very low energy X-rays, those 0 to 10 keV, don't even make it out of the X-ray tube. They're in the primary beam, possibly, but we catch them before they come out of the tube if they're made in the interactions of our photoelectric, our Brewster-Long characteristic. So if the tube makes very low energy X-rays, we try to catch them in that filtration. So now we have another interaction that could happen. This is called Compton scattering. This is going to happen between 20 to 40 kilo electron volt. So anything in that range of our beam energy is going to probably result in a Compton scattering. So this is happening a lot in X-ray interactions with our patients. Compton scattering, we say, is not good, but we can't stop it from happening. So in this interaction, the X-ray photons going through the body, interacting with some sort of tissue in our body, so a tissue atom, and it happens in an orbital electron. Generally, we say the middle or outer shell electrons, and it knocks them out. So it's knocking out electrons. And when it does that, that incoming X-ray photon loses up to 1/3 of its energy, and it's changed into a new direction. So it kind of gets bumped, like bouncing off of that electron, knocking it out, losing some of its energy in the process. So if it was 100 kiloelectron volts, we'll say 75. What if it was 75 and it loses 1/3 of its energy? So it's going to have 50 remaining. So that new photon in that new direction that's moving on, or that same photon that changed direction, is now lower energy. And we'll see this in a drawing in a minute.
And this is still taking place within the tube, the stuff that we're talking about?
This is all happening inside the patient, in us. We were the patient.
Okay.
So these are atoms that are getting hit by the photons coming out of the tube. So our primary beam's coming through and stuff is happening in the body. Good question. So these little waves, remember a photon is drawn like a wave, an electron is a straight line, and then it hits and then a photon's made. So if you see a drawing on a test, or we ask you to draw this interaction, you need to have an X-ray photon coming into the atom in a waveform, hitting an electron, changing direction, lower energy. So see how this one's higher energy? The waves are close together. The new photon, the waves are further apart, because when that is an electron, it loses 1/3 of its energy by knocking this electron out. So the new photon scattered in a new direction is considered the Compton scattered photon. Now this has another step to it we don't really worry about too much, but that scattered photon could hit another atom and cause another interaction. Then it loses more energy and scatters off in a new direction. So that's just having it happen twice. It's the second Compton effect. But we're only concerned really with this first Compton interaction. This is just showing you that this could possibly happen in the body. So we could have multiple scattered photons happening. When they change direction, they are no longer going down from the tube through the patient. They're coming off the side of the patient, up in the air, sideways, any direction. They can be scattered. So these are called scattered photons. We just initially drop off the word Compton, but when we're saying a scattered X-ray photon or X-ray scattering, this is what we're talking about. So whenever you guys were talking about scattering the other day, and I kept saying, don't say scattering, this is why. Because Compton scattering is a scattered photon, an X-ray photon that was coming down from the beam, and now it's scattered off into a new direction. That's Compton. And it happens with middle or inner shell electron normally, because they're usually pretty high energy. They're going to knock out one of these electron shells. Middle or outer shell electrons. When it's inner, something else happens, sorry. So there's three things that happen. Remember, an adding or removing of an electron is called ionization. So this atom has become ionized. It's no longer stable, and those little electron vacancies are going to scattering is going to happen again, but we don't really talk about that too much. But this electron that's ejected is called the Compton electron, and it leaves, and then it could interact with other atoms. So that's another secondary thing that happens. We are mainly only concerned about the primary interaction. This incident photon, that means the incoming photon comes in, is deflected in a new direction, and it is now called Compton scatter. It loses 1/3 of its energy. That photon can go through and interact with other tissues, or it can come out of the patient. It could also come to the image receptor, depending on whatever direction it was when it was scattered.
So when that the high energy photon hits outer or mid electron, when that electron is booted out, that atom that it originally came in contact is ionized.
Correct.
Inside our body.
That's when damage could come to it. That could possibly cause a cancer later on, and that's where it gets into the DNA and stuff. We're not going to go that far right now. So Compton scattering is usually thought that some of it's going to hit our image receptor. When that happens, these are bad energies. They are not coming through like they were supposed to and produce an image to our X-ray plate. Because they are such low energy, they produce this thing we call fog on the X-ray plate. And that's a grayness, and overall, like looking through the fog at a building, it kind of looks grayed out. So we call it fog on our image. Compton scattering is what causes fog on our image. And we want to reduce that as much as possible. And we have things we're going to go over in another chapter that we use to reduce fog. And grids is our one big thing. We do other things too, but Compton scattering is the most prevalent interaction between X-ray photons and the body in our imaging and diagnostic imaging. It's responsible for scatter that fogs the image. So that makes our image look bad. Compton scattering can happen in soft tissue and bone. Can happen in any type of atom in the body. The probability of Compton happening is related to the energy of a photon. So here's where we get interesting. Just think about our beam again, from 0 to the maximum kVp we set. That's how much energy our beam's going to have. The higher we go up, the more different energies we're going to have of the beam. The higher we go up in kVp, the average energy shifts to a higher average energy. Everybody got you? Good there. So if we go from 50 kVp, our average energy of the beam is 1/3 of that. So we're down on the lower energy range. If we go to 75 or 100 kVp, our average energy moves up. So with our average energy of the beam moving up, we're having more photons being higher energy. More photons being at that higher energy level are going to have more photons going to interact with those atoms shells and cause more Compton scattering. So just think the higher the average energy, the more likely we're going to have more Compton. So as we increase our photons energy or we increase our kVp, we're probably 100% increasing Comptons. More Comptons are going to happen. So we don't want to always say the highest kVp. We want to have a good kVp for the part we're X-raying that's in the best range possible without going to the max, because the higher we go up in kVp, the more Comptons we're going to make, more fog, more scatter. And the higher we go up with photon energy, the less likely a photoelectric interaction is going to happen. But we'll talk about that more because we haven't talked about what photoelectrics are. So remember Compton interactions, that scattered photon loses 1/3 of its energy. So that original photon still has 2/3 of its energy to come through. So that's if it goes in a new direction, it has, sorry, I said that backwards tonight. It loses 1/3 of its energy, so it has 2/3 of its energy coming off the patient, that scattered photon. So that's why we want to protect ourselves with time, distance, and shielding, because we are probably going to be the ones standing there in a fluoro case where scattered photons are coming off the patient at us. That's where our dose comes into play. So number one exposure for us, occupational dose, is Compton scatter.
Ms. Love, I have a question. You said the probability of the Compton effect goes down when the X-ray energy goes up, or is that vice versa?
It goes up. If we increase our energy, we're increasing Compton. They're
Okay,
together.
Yep. I watched a YouTube video last night and I have it pulled up on my computer that says the opposite.
So it says if you increase your energy, you decrease Compton?
Yeah, I'm going to take a picture of it. I'm going to send it to you. Yeah, that's, yeah.
Ooh,
So
that's
not
crazy.
true. Not true?
No, if you increase your kVp, you're increasing the average energy, more Compton. Yeah, 100%. So when we go up in KVP, we're making more Compton, we're making more scatter. Higher KVP. So photoelectric effect, so it's in our diagnostic range. This is our next interaction. 20 to 120 kVp, that's our diagnostic range. Generally, we don't go as low as 20, somewhere around 50. And we're talking about interactions with the inner shell orbiting electrons in the atom and our tissue of our body. So when photoelectric events happen, the incident X-ray photon, meaning the incoming X-ray photon, the energy of it must be equal to or greater, slightly greater, than the orbital shell's binding energy. So here's a picture of what photoelectric looks like. So we're thinking of it as an incoming photon coming in, knocking out a K shell or inner shell electron, usually K shell we're usually thinking of, and getting rid of that, it loses all its energy. It becomes absorbed. So we usually call this photoelectric absorption. So if it's equal to or slightly greater to that energy of that binding shell of our atom, then it's going to knock it out and lose all its energy doing so. So this is photoelectron. When it's ejected, that's this little electron's name, photoelectron. But really what we want to knock at and know is this incoming photon loses its energy here when it knocks out this electron. Now, these other photons, secondary X-rays, are coming in and filling in those vacancies. That's cascading, similar to what happens in characteristic in the tube.
I was about to say, it's just like a characteristic
Exactly.
interaction, but inside a patient.
Photon instead of an electron. Yep. So if we
still have the binding energy, is the same as the other ones? Are all binding energies?
That's why KVP ranges come into play, because every body part is made up of different atoms. So bone is different than fat and muscle and so forth, and water. So everything has a different binding energy on the atom. And it also depends on what's going on in the patient. Do they have a disease process going on that's deteriorating their bone, like osteoporosis? Their bone's not going to be the same as a young, healthy person's bone. So their atomic.
So for this, we don't have to know like a specific number. This time it's just, it has to be equal to or slightly above the binding energy.
Correct.
Okay.
Yeah.
Okay, so in this process, the photon is completely absorbed by the electron, and then the electron like disappears and becomes a photoelectron, like kind of like
it's knocked out. It could go on and hit something and do something, but yeah.
Okay.
Yep. It just has that name, photoelectron. I've never heard anybody talk about that name very much. So this is called photoelectric absorption, when that incoming photon is absorbed in the body. So this is what gives our patient dose to our patient. X-rays being absorbed in the patient is giving the patient dose. So we need absorption, because if we didn't, we wouldn't have any areas of white on our X-ray. If we just took an X-ray and all the X-rays went through, nothing was absorbed in the bone or something, it wouldn't show up. We wouldn't see the fingers or the bone. So we need photoelectric effects to happen. This is where our factors of setting our technique on the control panel is our main job responsibility. Setting the right KVP and mass for the body part to balance image quality and patient dose. So if we select a high mass, we're selecting a lot of photons. If we select the right KVP for that penetration of that part, we're selecting about how many of those photons we're going to have absorbed in the patient.
And you said for this photoelectric interaction, it's most likely to occur when the photon hits the K shell?
Yes, we're talking about K shell usually, yeah. So they say inner shell vacancy, making the atom unstable, because now we say this atom has been ionized and cascades are going to happen through secondary X-ray photons coming out. these are such low energy, they're probably going to be absorbed by the body or have another photoelectric event happen in the body, contributing more to patient dose. So those secondary scattered aren't going to make it to the image receptor. So the probability of a photoelectric interaction happens when the energy of that photon interacts with the atomic number of the tissue that they're going to interact with. So we have all these different tissues. We don't know the binding energy 100% of every single little part in the person that we're x-raying. We only kind of have a range that we go with. So you don't have to memorize that like Jess was asking about. For photoelectric interactions to occur, the incident X-ray photon energy must be greater than or equal to that inner shell's binding energy of that tissue that we're X-raying. The greatest number of photoelectric interactions are going to happen when that X-ray energy is really close to that binding energy of that tissue atom. So that's what we're hoping for and we're shooting for with our range of energies that we're producing in the tube. We're not just producing one energy, so we're having a variety. So some are going to make it through, some are going to be absorbed, and we know this. In this process, we're going to talk a lot more about tomorrow, differential absorption. So that is the difference between the primary beam coming out of the tube, some of those photons being absorbed, and some of those exiting. This is differential absorption because we know some of our photons are going to be absorbed. And then we also know some are going to be scattered through Compton scattering. So the process of differential absorption is going to be the difference between our primary beam and our exit beam. We need this differential absorption to happen in the body, or else we wouldn't have a different shades on our X-ray plate. Areas with white, like where the spine is where most of our X-rays didn't make it through, which is super crazy on this picture. They have a couple that made it through. That would be an area of black or gray. So depending on how much was absorbed, it's going to be what we see on our X-ray plate. I just realized they did that in this drawing, that they put the X-rays coming through the spine and the rest not. Mostly the spine and the bone is going to absorb X-rays, and everything else is going to happen as they're coming through. But this is just showing you that we have only 2 photons coming out when we had 6 photons going in.
You said it was the difference between the primary beam and what?
The remnant or the remainder, the leftover X-ray beam. It's the process of absorption.
And the photons that are getting absorbed by the part, that's where the photoelectric is happening?
Photoelectric is happening, yep.
Okay.
And these that are coming off scattered are
Compton. Okay.
So I don't know if you've seen X-ray shirts say straight out of Compton. We're talking about Compton scattering. We say Compton's bad because you don't want to go to Compton. Everybody's going to scatter when the gunshot goes off. Depending on what scenario you want to remember it by. This is something called shades of gray. And this is one of our objectives for this chapter. I don't know why it was in with this one. On our X-ray, you're only going to be seeing the shades of gray that is being projected onto that image. I could take 2 or 3 different X-rays with different KVPs and penetration and come up with different shades of gray. So this is called our scale of contrast. So if I go 1, 11, 5, and 55, there's 4 different shades of gray. But if I go 50 through 100 here, there's a lot of different shades of gray, 10. And then the same thing here on this row. So if I have like just these 15, 25, and 75, I like looking at these 3. There are big differences between them, right? You can definitely tell the difference between these 3. But if I look at these 3, 60, 65, and 70, not a lot of difference between them. So we call this, when there are big differences between them, high contrast, a high contrast image. More black and white, easy to see the differences. But when we get into these that are similar, we call this low contrast image. because the matter between them absorbed equally, almost the same, and they look alike, slight differences between them. So low contrast, high contrast.
Ms. Love, is that the same PowerPoint you have on? Because I don't see this page on it.
These are not on there.
Yeah. Mine only goes to 15.
I added these this morning for me to show you guys this.
Okay.
Yeah.
So low contrast has more to do with your ability to see clear differences in shades rather than high contrast, meaning everything's bright or something like that.
Correct. In the classroom, you guys may have seen on the wall, there's some paper. It's like toilet tissues with different shades on it hanging up by the board. When you go in there again, it's the the room with the 2 big windows with the portable machine in it that you guys were in for venipuncture up on the wall. So somebody made that for our scale of contrast. So when you have high contrast, we call that short scale, because the scale is short. Not a lot of differences between them, short scale. When you have close to the same ranges and hard to tell a difference, we call that long scale, longer scale contrast. So short scale is considered high contrast and long scale is low contrast. Those get super confusing. So long scale, lots of different shades of gray that are kind of similar. Short scale, big differences between them. High contrast, we can see the differences easier. The term contrast in the book, I don't know if it's in this chapter. It just says the differences between the shades. I think it's tomorrow, and we'll talk more about that tomorrow too. But I just wanted to introduce you today into this because it's on your objectives, because it becomes important when we talk about the 15% rule. So short scale, long scale. Short scale is high contrast, big, easy to see differences between the blacks and whites on the x-ray. So I always say a hand x-ray is high contrast, short scale. The bone and the soft tissue, that's all we have in there. Easy to see the differences between it, more black and white image. Long scale x-ray is the abdomen. That abdomen x-ray from the beginning, where the middle of the belly, you have all these things going on and slight differences in grays closer to the same shades. Not a lot of difference between them. Is longer scale contrast. That's low contrast. So even 35, 40, 45, 50, this is considered low subject contrast. It can be a section anywhere in here. I don't really see any difference between 13, 14, 15, 16. Slight differences. That's long scale.
I compare the two that you have to look at the image longer to tell the difference.
Oh, I like that. That's long scale. The shades are closer to being the same. So what does this have to do with KVP and the scale of contrast? So generally speaking, low KVPs are going to have a certain range of energy levels. So around 50 KVP, the average energy is 1/3 of that. So what is that, about 15? That's our average energy of the beam. Do you think with that low of an average energy, we're going to have more absorption in the patient or more Compton with that low energy? More likely, more of those photons are going to get absorbed. So that's going to be a lot of white. And either they're going to be absorbed or they're going to be transmitted with that lower energy. If they're transmitted, it's probably going to be on the sides of the finger where there's not a lot of anything there but some skin. And if they're absorbed, it's going to be in the bone of the hand. So at 50 KVP, we're going to have a short scale contrast, more black and white. But if I go up, I'm going to have more energies, more different shades are going to come out. So a longer scale of contrast. So the higher we go in KVP, the longer our scale of contrast is going to be. The lower KVPs is going to be shorter scale of contrast.
Can you say that again, please?
The higher we go in KVP, the longer our scale of contrast is going to be. We're going to have more different energies with different interactions in the patient. Lower KVPs is short scale, more absorption. This is going to be a lot of talk tomorrow and for the whole rest of the class on this. So how does the 15% rule play into that? If I increase my KVP by 15%, if you have a calculator, you can do the math. 15% of 70. Let me do it on my calculator. Anybody did it already? Because my phone's being slow. I always say 10 kVp. So 70 plus 15%, I got 80.5. So 10 kVp up is 80, so 80.5 and 80 is not that big of a difference. So if I go from 70 to 80 kVp, I'm going up 15%. Am I making my beam more penetrating? Yes. Hopefully everybody say yes. If I'm going up 15% in kVp, my energy level, average energy of my beam shifts to a higher average energy. So I'm going to have more of my beam penetrating through the part, more different shades of gray. So that's going to be a longer scale of contrast.
Meaning a lower contrast.
A lower contrast image, yep. Longer scale, lower contrast, good. L and L, that gets confusing. If I go down 15% in kVp, we can do the math. I would just say from 70, I would go down 10 kVp to 60. See what it comes out to on the calculator. 70 minus 15%, 59.5, pretty close to 60. So my teacher just said add 10 kVp or subtract 10 kVp. You're doing about the same thing as the 15% rule with math. So if you don't have a calculator, that's how you can do it. When you get to 100 though, you know 15% of 100 is 15, so you have to go up to 15 kVp more. But from the 100 down, about 10. So if I go down to 60 kVp from 70, I'm decreasing my kVp by 15%. When I do that, more likely my energy shifts down and most of my photons are going to be absorbed photoelectrically. So that means more black and white, short scale, high contrast. So the 15% rule affects contrast on our image, the scale of contrast. What else does 15% rule do? Number of photons that reach the IR. This is a different thing than contrast. This is quantity of photons. So if I have 100 photons that make it through and I go up by 15%, it is the same thing as doubling the mass. So that would be the same thing as now having 200 photons come through. Because the penetration is that strong when we change by 15% in kVp. We're making it that more penetrating.
So see, that's where like mass like indirectly affects quality.
You're thinking of it as not separate though. We're not changing the mass. We're doing this as effectively doubling the mass, but instead we just went up in kVp and changed our penetration of those same number of photons. We're just changing the penetration. But in our, you're saying it's the same as doubling mass. It's not doubling the mass though, it's just doubling those same number of photons. More are going to get penetrated because now their energy went up. So that's where it gets confusing.
So photoelectric absorption, that shows up light on the X-ray or dark?
Light, good question.
Okay, yeah, for sure.
If they're absorbed, they're going to be an area of white if they're totally absorbed. So how do we get gray? This gets a little confusing. So if we have millions of photons coming through out of the tube, we're talking about it in small numbers and drawing it in small numbers. If I have an area, I'm going to try to think of somewhere that has more shades than the hand, in the shoulder. And I have muscle here, and I have a space where my glenoid fossa is, where my shoulder connects. And then I have a humeral head that's bone, and then I have a clavicle here and some lung. I have a bunch of stuff here that's going to have ability to interact. The part that's going to show up a little bit lighter, not either black or white, because it's not totally absorbed, is where the muscle is here in the armpit area. So that's going to be areas of gray. Some of those millions of photons are going to get absorbed. Some of them are going to still transmit through, but they're not 100% coming through like they are where the area of white is, where the joint space is, because there's nothing there to absorb them. That joint space shows up black. Where the bone is a white spot, because the bone and the humeral head absorb most of my photons, so it showed up white. But in this area of the armpit and the muscle tissue here shows up a grayness on a shoulder x-ray. That's where some photons made it through. Some of those photons got absorbed. So that's where our shades come into a play on the abdomen, and the liver sometimes shows up. Sometimes you can see an outline of a kidney. It just depends on the percentage of photons that made it through, if it's a gray area or not. So that's where our long and short scale comes in, depending on how penetrating it was and how many of those photons made it through. It's a lot. We're going to get into it more. This is just the intro.
So the higher the atomic number, atomic number affects photoelectric effect. So the higher the atomic number, the more X-ray absorption.
Yes.
So that's why you can see bone is lighter than fat.
Yes.
Okay.
That's tomorrow's chapter. Yep. Yep. And that's where differential absorption is going to come in. So we have this formula we do called the maintaining exposure to the IR when we change our KVP. So Michael, this one's going to be for you with that mass stuff. Let me just type on here. So if I have 70 KVP and 20 mass for an exposure, and I go up to 80 KVP, which is the same as doubling my mass. So now that would be like 40 mass. I don't want that. I don't want that many photons. It'll be too dark, too many. I'm going up in KVP. I'm making more penetration. I'm making essentially doubling the amount of photons come through. So to make the same exposure to the IR, to make it about the same amount of photons that make it through, I have to half my mass for the new exposure. To maintain the exposure, to essentially say I have the same number of photons coming through. This is a formula we use called the maintaining exposure formula. I'm not going to make you guys do this formula in this class, but Miss Dean will in the next class. So I just talk about it in relation to why when you go to clinic, you see techs adjusting KVP and bringing mass up or down. That's why. They're using their penetration for their quantity. In their head, they're doing the same thing as doubling the mass, so they cut their mass in half. Or you have to remember when you're doing this, you're changing your scale of contrast. So you don't always want to do it. Sometimes our X-ray came out too light, and instead of going up in KVP, because we know we're going to cause more scatter, we double our mass to make double the amount of photons come through. So all three of these are the same amount of photons. 70 at 40, I'm sorry, not the same amount. This is doubling the mass. This is essentially keeping the same exposure. Let's do a different one to say, what else could we do that could be the same as 40 mass? We could say 80 KVP and 20 mass. These last two have the same amount of photons. The first two, same amount of photons. Because if you go up in KVP, you're essentially doubling the photons coming through. So to keep it the same, we half the mass. And again, this is a formula that Miss Dean's going to teach you guys about using it next month, next class. Just wanted you to understand the reason you may see techs alter their technical factors and what they're doing in clinic. This happens usually when you're in a portable situation too, and you're not in the X-ray room where you want to adjust from what you would normally use because of certain factors in the patient, or your X-ray didn't come out right and you need to make some changes. It needs to be darker or lighter or more penetrating, and you knew the mass should have been this, but if you use that same mass, it's going to be too dark. So we're going to do some exposures in the lab with this. Go ahead, Michael.
So we have physics 2 next month?
No, your next physics class is not until you come back from clinic. So you'll go to clinic and then you'll come back and go into another physics class.
Yeah, but not next month.
Not next month,
Yeah.
no.
What do we need to know for this right now for like our exams?
Now, and for your exam, just know that changing your KVP is essentially doubling the photons that are going to reach the IR. Yep, that's it. So the formula that's on the objectives for today, I'm not going to have you guys do the math for that formula. Just knowing that KVP going up by 15% is changing the exposure to the IR. 15% rule we will have.
Going up by 15% changes the what? Yeah.
The exposure. So that's the first part of knowing what the exposure is going to be for this formula. If you understand that, you'll be ready for this when she talks about it in your next physics class. So increasing by 15% is effectively doing the same thing as doubling your mass or doubling the exposure, because you're making that beam that much more penetrating, more energy, more photons are going to come through.
But that's only if you're increasing KVP.
Yeah,
If
and
if you decrease the KVP, that has nothing to do with doubling mass? Or
opposite way. Same thing happening, but less penetrating. So halving the mass instead of doubling it. Yep, good question. Going up or down in 15% changes the penetration of the beam. So you're either going to be having less photons or more photons, depending on which direction. So more photoelectric or more transmission. Transmission means X-ray photons pass through the part into the film. I think there was one more thing in the chapter, and we've talked about this before. It's the very last page. Chapter 7.
Absorption versus
radio opaque and radiolucent. They're bold words on page 8. So I think we hit on this when somebody asked a question a minute ago. I think it was you, Elizabeth, that talked about the bone. Structures appear lighter on our film or a white area because they're absorbing X-rays. So they're considered radio opaque. So less dense things have a lower probability of absorption and they're radiolucent. So the lungs, air-filled lungs don't absorb anything. X-rays pass through them easily. So they're considered radiolucent. Oh, somebody's attention this morning. And that is our differential absorption in a nutshell, actually, talking about those two differences. And we're going to talk more in depth about the body and all the parts in it tomorrow. It's called image production chapter, but it's more about this absorption that's happening. And the macro level, that's the part you can X out. We're not doing DNA in this class.
And would you say radio opaque is more related to high contrast or low contrast, or is it? Or is it? There's too much else involved than just
on what the part is. Yeah.
Okay.
So it depends on how much radio opaque things are in that area and what our KVP and stuff is. So yeah. Short and long scale contrast are more to do with, you can take the hand and do 4 X-rays of it, and one can be more shorter scale and longer scale than the other, depending on the penetration of the beam. So we could use different KVPs. So I'm going to have somebody do that for your project, one of the groups, and show us that. Oh, hey there. So that's it for today. I was going to go over some of these questions on the objectives to make sure we got everything.
in the outline, the objectives that we need to outline, that's under week 1, and you've got Monday, Tuesday, Wednesday, Thursday. Like all those numbers we outline?
Yep, so if you just take today's, what's the controlling factors for radiography? Type that out. So what's the inverse square law? We did that last week. I don't know why I left it on for this one, but if we
diminishes by the square of the distance from the.
Yeah, so just want to know that you can still do that. Yes, because I had some of chapter 6 as a review this week too. So here's our main ones, these 1 through 15s, but making sure you don't forget that. X-ray interactions, photoelectric and Compton, those are our main 2. Classical or Thompson, we get rid of those in the filtration. So they're not our main 2 that you're gonna be tested about. Now, don't forget about them because they will be on the registry and I might have one on the exam. What is beam attenuation? We didn't use this word. Attenuation of the beam just means that it was absorbed or removed. So photoelectric effect is effectively beam attenuation, removing some of our beam. Exit radiation, that's our remainder beam coming out of the patient, that's exiting the patient. So it's going to be less than our primary beam. Some of the energy levels coming out of the patient are not going to be the same energy as the primary beam. The wavelength of the energy has been changed as it's coming out through Compton scattering, for example. So the composition of exit radiation is the energy is not the same. Exit radiation is patient has absorbed some, so we don't have the same number. So a couple of different things you could say about exit and how it's made up of. Now, do some of our X-ray photons come through the patient and don't interact with anything and come through and hit the IR? Yes. Another one that was from last week that you should be able to talk about is the anode hill effect. We want the thicker part under the cathode side because more photons are going to penetrate that side. Scattered radiation on an image, easy one, it's just fog. It's an area of gray or fogginess on an image. Scatter is bad for our image. The process of creating our exposure. So this is talking about the X-ray getting to the IR, exposing the image plate. So that process is through photoelectric and transmitted X-rays hitting the IR. So we're going to get different shades of gray depending on how many photons were absorbed or transmitted through. Ionizing radiation interacts with matter. 2 things, either outer shell or inner shell electrons get knocked out. That's when it's ionized, the atom. So outer shell ones are Compton, inner shell are photoelectric. That's our 2 ways that the atom or the matter gets ionized. Contrast. 2 things with contrast. We have short scale and long scale. So on our image, we're either going to see close shades together, that's long scale, or we're going to see big differences in the shades, that's short scale contrast. The quality of our radiograph. That one we can't do today. Number 9 should be on tomorrow. I'm going to move that one. Because the quality of our radiograph is dependent on the patient, the parts of the patient, whether there's a lot of fat in there or what it's made out of. That's with differential absorption. So we'll get into that a lot more tomorrow. Methods to get our level of radiographic contrast. So what you guys know now is that is by kVp. The penetration of our beam is going to change the energy of our beam, how it's going to be interacting in the patient to either be absorbed or pass through. So that's going to change our scale of contrast. Higher kVp, longer scale of contrast. Lower kVp, shorter scale of contrast. Changes in mass and kVp. For receptor exposure, that's the 15% rule. If you increase kVp by 15%, you're going to have more exposure to the IR. How much more? The same as doubling the mass. Says there's people in the waiting room. Basic calculations using math. So this, I wanted you guys to be able to know how to figure out math. So glad I went over that one day with you guys. Let's do that on this PowerPoint. Can you still see my slide?
Yeah.
All right, so I wrote it on the board last week. Mass is MA milliamps times seconds. And that equals mass. So on our calculators, because we will have some of these where you guys have to calculate out the mass. In our room, you do the dial, and you can select 150 MA. And you can put it at like 1/16 of a second. Let me get my calculator back out. And it's going to do this for you and tell you your mass value. That is 0.0625 seconds. So I'd have to do 150 times 0.0625. And that's going to give me my mass. 9.3. So we'll just say 9 mass.
How did you get the 0.0625?
1 divided by 16, 1/16 of a second. So 1 divided by 16 gave me the 0.0625.
Okay, thank you.
You're welcome. So mass is MA times the time, or times seconds. So you want to be able to calculate mass, manually calculate it out. Now, is there different values that could give me 9 mass? If I changed 200 MA, probably.
Miss Love,
Yeah.
where did you get the 1/16 from?
I just made it up. I said it 1/16. Hey, baby. This is my grandbaby. You want to say hi? Oh.
Hi.
And this morning. Here's a little boy. Say hi.
Miss Love.
Yeah.
So what you're going over, is that in a book somewhere where I can read it to like kind of, because it's going over my head, I'm being honest.
There is a chapter somewhere. Let me look it up.
There's a chapter somewhere.
Let me find it where it says how to calculate mass. I don't know if we're going to go over that chapter in the book. So.
But for the Monday, Tuesday, Wednesday, Thursday numbers and objectives, all that together in an outline is the homework that's due Thursday at midnight.
Correct.
Okay.
Milliamperage. Let's see what's in here.
I'm gonna go see like this.
I don't know if it's in this book or not. 131. It's on page 131.
And just making sure the outline from last week is due this week, right?
No, there was no outline that you had to do last week for this week. Nope.
So the outline is where?
It's under your homework folder for this week.
The outline is what you're making.
Yeah.
Of the objectives of, if you click on week 2.
Yes.
Yeah.
And you scroll down, it says week 2 objectives, and it's got Monday, Tuesday, Wednesday, Thursday.
Yeah, that's your homework for the week.
Okay.
So all of them right now for today. So all you have to do is rewatch this and you can make your outline.
So pretty much just answer the questions in the form of an outline.
Yep, that's it. Make your own
Yeah, gotcha.
Number 12, perform mass. That's what I'm going over now. So page 131 shows you the little box on this math formula. MA times seconds equals mass. So let's do 200 MA. And we're going to multiply it times 0.25 seconds. Let's see what our mass will be. So 200 times 0.25.
Is it 50?
Yep, that's what I got, 50. So 50 mass. So now what if I wanted to do 100 MA and still get 50 mass? I'd have to do 0.5 for my seconds. Make sure I did that right. 100 times 0.5, I still get 50 mass.
Yeah, 50.
Why my fingers are off by 1? So you can do multiple different time and MA and still get the same ending mass. So mass is how many photons we're boiling off. So that's on the how to calculate mass question for your objectives. Just knowing basic calculations for mass. So inverse square law, receptor exposure, and the 15% role and how they affect the image exposure. So if we're thinking about inverse square law and how it affects receptor exposure, if we're at 72 inches and we move into 40 inches and we use that same mass, 50 mass, same KVP, 70 KVP, are we going to have the same receptor exposure at 40 inches that we had at 72? Based on what inverse square law says no. The closer you are, the more intense the beam's going to be. So by square of the distance, so almost 4 times more when you come into 40 from 72. Almost. We're not quite starting at 80. But just knowing that concept, I'm not going to make you do the calculations for changing your exposure factors. We would have to reduce our factors a lot if we were at 72 and we used a technique and we brought it into 40 and we didn't change them. We're going to have a really dark image because we're getting about 4 times more the exposure. So just knowing that concept of inverse square law. I know, go let him in.
So the inverse square law is the closer you are to the IR, the better the quality of the image.
The quality of the image, we're talking about the exposure of the beam. So we're going to have a lot more exposure at 40 inches than 72 if we use the same thing and didn't adjust our technical factors. The maintenance formula, just don't worry about that one. Not going to make you guys calculate that. We used to, but Miss Dean said she would do that next class with you guys. 15% rule, we know that if we increase by 15%, we are getting effectively penetration-wise more penetration. So we're doubling the number of photons coming through. So see how changes in 15% and how to adjust that for contrast? Don't worry about it. If you increase 15%, are you making your beam longer or shorter scale contrast?
Longer.
Longer, so it's going to make a longer scale of contrast. If we do decrease of 15% KVP, we're going to have a shorter scale of contrast. So we may say, what about changing by 15% calculation? You can do that on your calculator or you can do it in your head by about 10 KVP. We say 60 KVP and we increase by 15% to 70. If you do your calculator, it'll probably come pretty close. Let's see what mine tells me when I increase by 15%. 60 plus 15% is 69. So close enough, 70. So defining contrast, that's the number of shades of gray. The controlling factor, we're just going to say for now that you know it, is KVP. If we increase KVP, we're increasing contrast. Decrease KVP is decreasing contrast. And that's
It actually says you need to list the, or we need to talk about the controlling factors for radiology. Do you just want to do KVP or do we need to do that in mass?
in mass at the top. The controlling factors is mass.
Yeah.
Yep, that both of them. Mass controls quantity, KVP controls quality. So if the penetration is what controls our contrast, how much penetration effectively tells us if it's going to be photoelectric or Compton. And that's given us our shades of gray or our scattered photons on the board on the IR. Scattered photons don't usually make it to the IR. So that's taking away some of our primary beam, right? So that's why it's going to change our contrast if they scatter. Photoelectric effect absorbs our photons, so those photons aren't making it to the beam. So that's going to be a shade missing on our shades of gray, a white area. So that's why it affects our contrast. So effectively, photoelectric effect affects contrast. Compton affects contrast. So a lot today. Review this. It should be up probably in the next 45 minutes. Usually takes a little bit for it to download, and then I'll put it to YouTube so it'll save it forever for us. Any questions? So we went over all the objectives, so you can make your outline based on that, put it in your own words. Okay, guys, so nothing really due today. Just make sure you start working on those objectives every day this week so you have it done by the end of the week and you have a good overview for the test on Friday. See you guys at 8 on campus tomorrow. Bye.
Bye.
Bye.